There is an animal at the bottom of the ocean that looks exactly like something you have seen before. You know the shape instantly. 7 pairs of legs, segmented armored body, antennae, compound eyes. You have seen this animal in your garden, under rocks, in damp corners of basements. It is a woodlouse, a pill bug, the small gray thing that rolls into a ball when you touch it. Now imagine that exact animal. Same body plan, same armor, same compound eyes staring directly at you, except it is 2.5 feet long, and it is crawling across the pitch-black floor of the ocean at 2,000 meters below the surface. The giant isopod is real. It has been real for 160 million years, and the more you learn about how it actually lives, what it eats, how long it survives without food, what it does in the dark at the bottom of the sea, the more unsettling it becomes. Isopods as a group have existed for approximately 300 million years. They appeared during the Carboniferous period, before the dinosaurs, before flowering plants, before birds existed in any form. The family Cirrolanidae, which includes the giant isopod Bathynomus, branched off and colonized the deep ocean somewhere around 160 million years ago. 160 million years ago, the supercontinent Pangaea was still breaking apart. The Atlantic Ocean was in its infancy. The Indian Ocean did not yet exist in its current form, and the ancestors of the giant isopod were already settling into the deep seafloor, already developing the adaptations that their descendants still carry today. They survived the asteroid impact 66 million years ago that ended the non-avian dinosaurs. They survived every major oceanic anoxic event in Earth's history periods when large sections of the ocean lost oxygen and mass extinctions followed. They survived the ice ages. They are still here, still doing exactly what they have always done. In the dark, at the bottom of the sea, the giant isopod was formally described by science in 1879, when French zoologist Alphonse Milne Edwards examined a specimen collected from the Gulf of Mexico. He named the species Bathynomus giganteus, Bathynomus meaning deep dweller, giganteus meaning exactly what you think it means. Before that specimen arrived in 1879, deep-sea biology operated on an assumption proposed by Edward Forbes in the 1840s, the Azoic hypothesis, the idea that the deep ocean was too cold, too dark, and too pressurized to support life below 600 meters. The giant isopod's arrival and a research collection helped begin dismantling that assumption. The deep ocean was not empty. It had simply not been looked at properly. Let us understand what we are actually looking at. Bathynomus giganteus is the largest known species of isopod. The maximum recorded specimen measured 76 centimeters in length, 2.5 feet, and weighed approximately 1.7 kilograms. Most adults range between 19 and 37 centimeters, still large enough that holding one requires 2 hands. The body is divided into 3 sections: the head, the perion, and the pleon, covered by a series of overlapping armored plates called tergites. This armor serves multiple functions. It provides structural rigidity in an environment where pressure at 2,000 meters exceeds 200 times the pressure at the surface. It provides physical protection from the few predators that operate at abyssal depths. And when threatened, like its tiny garden relative, the giant isopod can curl into a near-perfect ball, tucking its 7 pairs of legs inside the armored exterior and presenting nothing but hardened plate to whatever is threatening it, a defensive sphere of chitin and calcium, at 2.5 feet wide, rolling on the ocean floor. Its compound eyes are among the largest relative to body size of any isopod species. They are fixed. The giant isopod cannot move its eyes independently, but they cover an extremely wide field of view, allowing detection of movement and light across a broad arc simultaneously. In the near-total darkness of the deep ocean, those eyes can detect bioluminescent flashes, the cold blue light produced by other deep-sea organisms from considerable distances. This matters because bioluminescence often means food is nearby. It has 2 pairs of antennae, one shorter pair for close-range chemical sensing, one longer pair for detecting vibrations and water movement at distance. It perceives the world primarily through chemistry and vibration. Vision is secondary. Smell, or the chemical equivalent of it, is primary. Here is where the giant isopod stops being merely interesting and starts being something that genuinely sits with you. The deep ocean is not a productive environment. Food at 2,000 meters is scarce by the standards of almost any other ecosystem on Earth. The primary food source is marine snow fragments of organic material that drift down from productive surface waters above. By the time marine snow reaches abyssal depths, it has been consumed and reconsumed multiple times during its descent. What arrives at the bottom is a fraction of what began. Giant isopods deal with this reality in two ways. First, they are opportunistic scavengers. When food arrives in whatever form, they eat aggressively. Researchers have observed giant isopods feeding on the carcasses of large animals, fish, squid, whales that sink to the deep seafloor. They consume large quantities rapidly when food is available, eating until the body is visibly distended. The digestive system stores nutrient reserves in specialized tissue that can be drawn upon slowly during periods of no food. Which brings us to the second way they deal with food scarcity. They wait, not for days, not for weeks, for extraordinary periods that initially seemed impossible to researchers who studied captive specimens. In 2014, a giant isopod held at Toba Aquarium in Japan died after refusing food for 5 years and 2 months. 5 years. The animal had been offered food regularly standard marine invertebrate diet throughout its captivity. It refused every offering for 5 years and 2 months, and then it died. Not from starvation in any conventional sense, its body condition remained relatively stable throughout the period. Researchers believe the animal may have been consuming its own stored reserves throughout captivity, and that the captive environment, lighting, water chemistry, temperature may have suppressed feeding behavior that would normally activate in response to specific environmental cues. But 5 years without a recorded meal, in a controlled facility, with food offered consistently. That is not normal biology by the standards of any familiar animal. That is deep ocean biology, where patience is not a virtue. It is a survival strategy. The obvious question: why is it so large? A woodlouse is a centimeter long. The giant isopod is 76 centimeters. That is not gradual scaling. That is a different category entirely. The answer is a phenomenon called deep-sea gigantism, the tendency for certain invertebrate species to grow significantly larger in deep, cold ocean environments than their shallow water or terrestrial relatives. It has been documented across multiple taxonomic groups, not just isopods, giant amphipods, giant sea spiders, giant tube worms, giant ostracods. The pattern appears repeatedly across unrelated lineages. The leading explanations involve several interacting factors. Cold water slows metabolism. A slower metabolism means slower cellular aging. The body accumulates damage more slowly, which allows it to continue growing for longer before the systems that regulate growth begin to fail. In warmer surface waters, metabolic processes run faster, organisms mature faster, age faster, and hit their growth ceiling sooner. In the cold, deep ocean, where temperatures hover between 1 and 4 degrees Celsius, that ceiling is reached much later. Additionally, reduced predation pressure in the deep ocean removes a key evolutionary constraint that keeps shallow water species small. In productive shallow ecosystems, being large means being visible. Visible means being targeted by larger predators. Natural selection in those environments favors smaller, faster, more cryptic body plans. In the deep ocean, where large visual predators are rare and encounters are infrequent, that pressure is reduced. Growing large has cost more food required, more energy to move, but without heavy predation, those costs are manageable. The result, over millions of years of evolution, is an animal that keeps growing because nothing is eating it fast enough to stop it. I want to spend a moment on something that does not usually appear in biological documentation. Why does the giant isopod disturb people so consistently? Because it does. Show a photograph of one to someone who has never seen it before and watch the reaction. It is not fear exactly. It is something more specific. Discomfort. A kind of low-level wrongness that people struggle to articulate. The answer lies in a well-documented psychological phenomenon called the uncanny valley, originally described in the context of robotics and artificial faces. The uncanny valley refers to the discomfort produced when something is almost familiar but not quite right. A face that looks almost human but has subtly wrong proportions triggers more unease than something completely alien, because the brain recognizes the pattern human face, then detects the mismatch, something is wrong, and cannot resolve it. The giant isopod triggers a version of this response. The brain recognizes the pattern instantly. Woodlouse, pill bug, garden insect, familiar, non-threatening. Small, then the scale registers. 2.5 feet. The pattern match breaks. The familiar shape at the wrong size produces a specific neurological discomfort, a signal that says, I recognize this, but something is wrong, and I do not know what to do with that. Add the deep ocean context, the darkness, the pressure, the abyssal environment, and the discomfort intensifies. Because the brain is now processing something it recognizes in a context where nothing familiar should exist. The giant isopod is not threatening by any objective measure. It moves slowly. It eats dead things. It poses no danger to humans it has never encountered. But the wrongness of the familiar shape at the wrong scale, in the wrong place, in the wrong darkness that is harder to dismiss than actual danger. The giant isopod has been crawling across the abyssal seafloor for 160 million years. It survived everything, every extinction, every catastrophe, every geological upheaval this planet has produced. It did it by being patient, by eating when food arrived and waiting for months, for years when it did not, by wearing armor that pressure cannot crush and predators rarely bother with, by existing in an environment so inhospitable that most life on Earth simply never went there. It is not dramatic in the way deep-sea predators are dramatic. It does not hunt. It does not strike. It does not have bioluminescent lures or zinc-reinforced jaws. It simply persists, in the cold and the dark and the pressure, long after everything around it has died and sunk to the bottom, where it is waiting, patient, unhurried, in the only environment it has ever needed. The deep ocean does not create monsters, it creates survivors, and the giant isopod is one of the most successful survivors this planet has ever produced. 160 million years. Still here, still crawling, still waiting for the next thing to fall from above. If this is the kind of content that genuinely interests you, the real documented natural world, stranger and more unsettling than anything invented, then you already know what to do. Subscribe, because there are hundreds more of these waiting. Every single one real. Every single one already out there, right now, in the dark.